Hello, this is Dr. Oz. So we were talking about economic production quantity models, EPQ, and we calculate holding cost. Here we say that Q over 2 because of average inventory is going to be the function of Q over 2 times 1 minus D over P. So this is what we have in terms of average inventory. And again, this 2 is the maximum inventory divided by 2 will give me the average inventory. So if I want to calculate the holding cost, of course, I need to multiply this value by holding cost rate per year. Okay. So in the next slide, again, I have setup cost is the same as EOQ model, number of orders, order cost per order. And this is what we obtained in previous slide. This is my holding cost. Whenever these are equal, you can follow the math here. That's the best combination in terms of finding the lowest total cost. If I do the math, you can see that the optimal quantity is 2ds over h times 1 minus, in parentheses, d over p. So let's do an exercise on this formula. So as you see here, we have d, just in the formula right here. We have setup cost S, we have H, we have small p and small d, right? So I can just plug these values into my formula and calculate my optimal production quantity or batch size, which is the square root of 2 times 1000 times 10 divided by H, which is 0.5, times, in parentheses, 1 minus D over P, which is 4 over 8. If you do the math, you will get around 283 products. That's the best batch size that will minimize my total cost. So the D, small d here, is 4, which we could calculate, again, the annual demand over number of days that we are working. So if the annual demand is 1,000 units, and if you are working 250 days a year, then I can calculate that as 4 units per day. Again, when we use the annual data, you can use annual demand rate here, annual production rate here. As long as they have the same unit measures of per month, per day, per year, whatever it might be, anyway, those units will cancel each other out, so you are going to be fine. So it doesn't have to be really small d and small p here. It could be capital D and capital production PR or whatever, however you denote it. Okay, so let's look at quantity discounts. This is the last thing I would like to talk about in this presentation. And if we order more, we can get a better deal. For example, if I order more than less than 119, my supplier is charging me $100. If I order 200 to 1499 units, then I will get a better deal. If I order more than 1500 units, then I get even better deal. So let's look at these quantity discount models. Again, in total cost, I have 3 components here: the ordering cost or setup cost, plus holding cost, plus production cost. Okay, setup or ordering cost, holding cost, and production cost. So then I know how to calculate my ordering cost, which is D over Q, number of orders per year, times order cost per order. This is my ordering cost, plus holding cost is this is a typical EOQ model. Q over 2 is my average inventory, times H normally is the holding cost rate. But if I don't know the H, and if I know instead the holding cost per unit per year, expressed as a percentage of price, and P, the reason is that I need to have the holding cost rate in terms of price, because I have different price rates here, as you see, so that my holding cost rate, H, will change based on the price, obviously. That's why I will replace my H here with I times P, all right? And plus production cost, which is production cost is product cost, sorry, is product cost per product times annual demand. That would give me the calculation. Okay. And my Q star is going to be very similar to EOQ model. 2ds is my numerator, but denominator this time is instead of H, it will be I times P, because I write H as I times P. So these are the steps of quantity discount models. First, we're starting with the lowest possible purchase price, and then calculate the Q star optimal order quantity until the first feasible EOQ is found. This is a possible best order quantity along with all price break quantities for all lower prices. Then we calculate the total annual cost, and then select the quantity that gives the lowest total cost. So, for example, if I run this EOQ model 3 times for this problem, one EOQ here, one EOQ here, and then one EOQ for this price range. And then I can find 3 best solutions. And those solutions, as you see here, this spot right here, this spot right here, and this spot right here. That's the lowest cost. And you can see the cost functions here, right? This is the cost function for the first price, which is less than 120 units. I can get the price of $100. And you can see this, the red line here is my second total cost function for per product cost of $98 per product. And it's the third product total cost function for product cost of $96 per product. And this, for example, the first total cost function, the lowest cost is right here, obviously, but that's not a feasible solution because why? I need to order anything less than 120, then I will get the price of 100 per product. So really, this is not a feasible solution. If I want to find the best feasible solution, I really need to move this way to, and which will give me the point right here. This is my feasible solution, and actually best feasible solution. And for the second total cost function, as you see here, this red one, it is feasible because the quantity here is between its feasible range, right? This is its feasible range, and this best solution falls in that feasible range, so it is feasible. And if you look at the green line right here, the best solution is right there, but again, the feasible region for green is right here. Again, for blue, the feasible region is right here, less than 120. That's why I need to move from here, from this dot to the feasible dot right here, where it's at the intersection of feasible region and total cost. And for red, it's already feasible, that point right there. It's already a feasible point, so this feasible solution. For green, again, it's infeasible. That's why this point right here, I need to find the feasible solution for that. That's the point right here. So because that's in the feasible region. Now I can compare this green dot right here with this red dot right here, and then this blue dot right there. So as you see, blue is the highest cost, and the red one gives me the lowest cost, and green is giving me the middle cost. So the best solution here is obviously go with the red line, which is order something greater than 120. I don't know exact number here in this graph, but it will give me the best feasible solution, which is optimal solution, which is $517,155. So if you do math in the next slide for the optimal quantity ordered for price range of $96, you would get 2DS, which is 2 times 5,200 times S, which is $200, is order cost, divided by IP, the holding cost rate here is 0.28%, times the price is $96, then you will get 278 units. But again, 278 units is not feasible because this $96 is only feasible when I order over 1,500. So I need to find, instead of 278, I will replace this value with the best solution, feasible solution, this green dot. I need to find this 1,500 because that's the feasible region that will give me the lowest cost for this function. So instead of 278 for that price range, I will choose 1,500 units, which is feasible. If I can plug this one into my total cost function and calculate total cost. If I do the same calculation for $98 price range, which is the feasible region is 120 to 1499. Let's see whether we will get feasible solution. 2 times D is 5,200 times S is again $200 divided by my holding cost rate, which is 28%, times $98. That would give me 275 units, which is in feasible region because $98 feasible region is between 120 to 1,500 units. So, and I can plug in that value into my total cost as well to find my total cost. And if you do that, you will see that the best total cost you get is order of 275 units, and then you will pay $98 per unit. Ordering cost will be this, holding cost will be here, product cost for this will be that, and then this, if you add these three to cost, you will get the best solution here. All right. So this gives the lowest total cost. So our answer is buy 275 units at the price of $98 per unit. This is it for this video. Until next video, enjoy supply chain management.